Swayam Prabha. Digital India. Educated India.
Welcome to lecture 34 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is Recursive Models and Indirect Least Squares Estimators. In the last two lectures, we discussed the identification of a particular equation in a simultaneous equations model. We have also derived the rank and order conditions for the identification, and then we discussed several examples. The order condition provides a necessary condition, but it is not sufficient, and then we must check rank condition if the order condition shows that a particular equation is identifiable. Then the next step is estimation of the parameters of a particular equation of the model. The problem in estimation arises in simultaneous equations models because on the right hand side as explanatory variables, you have some endogenous variables included, and those endogenous variables are correlated with the disturbances. So, if you directly apply the method of least squares for estimating the parameters, the resulting estimators are inconsistent. So, the problem is to obtain consistent estimators for the parameters. Anyway, we must check the identifiability before going for the estimation. Further, if the equation is unidentified, then of course, you do not have any option. You cannot estimate the parameters of such equation. But if the equation is just identified or over identified, then you require different estimation procedures for just identified and over identified equations. Before going to all these estimation procedures for the simultaneous equations model, we discuss a specific form of simultaneous equations model, that is recursive models or triangular models. Recursive models are a specific form of simultaneous equation models in which you get endogenous variables on the right hand side, but those endogenous variables appear in different equations recursively. Means say in first equation you have just one endogenous variable, say y 1. In the second equation, you have two endogenous variables, say y 1 and y 2, and so on. And the beauty of these models is that you can directly apply the method of least squares for estimating the parameters of these models. So, you do not face the problem of correlation between explanatory variables or the endogenous variables which are playing the role of explanatory variables in a particular equation and the disturbances. So, we will discuss the estimation procedures for these models. Then for the simultaneous equations model, we consider the just identified case, and for just identified cases, we are going to consider the method of indirect least squares for estimating the parameters of the model. So, first we consider recursive or triangular models. Now, the problem in estimating simultaneous equations models is that the disturbances and endogenous explanatory variables are correlated. So, if in a particular equation you have endogenous variables on the right hand side as explanatory variables, then because of the correlation between these endogenous variables and disturbances, if you directly apply the OLS procedure, then the resulting estimators are inconsistent. So, OLS method is not appropriate for the estimation. You require some alternative estimation procedure. But for recursive models, the OLS can be directly applied. So, suppose we consider this example, we have 3 equations model. So, the first equation is y1 t equal to gamma 1 0 plus gamma 1 1 x 1 t plus gamma 1 2 x 2 t plus u 1 t. So, in the first equation, apart from y 1 t, you do not have any other endogenous variable on the right hand side. In the second equation, y 2 t is equal to gamma 2 0 plus beta 2 1 y 1 t plus gamma 2 1 x 1 t plus gamma 2 2 x 2 t plus u 2 t. So, you have y 1 t here. Then in the third equation, y 3 t is equal to gamma 3 0 plus beta 3 1 y 1 t plus beta 3 2 y 2 t plus gamma 3 1 x 1 t plus gamma 3 2 x 2 t plus u 3 t. So, in the third equation, both y 1 and y 2 appear on the right hand side. Here y's denote the endogenous variables and x's denote the exogenous variables. One thing you must notice that in the first equation y 1 appears, in the second equation y 1 and y 2 appear, in the third equation y 1, y 2 and y 3 appear. It does not matter which exogenous variables are included in different equations, because as I mentioned in the previous lectures, gamma does not raises any identification issue. So, if first equation has x 1 x 2, second equation has x 1 x 2 x 3, or the second equation has x 1 x 2 x 3 x 4 x 5, it does not matter. Now, suppose we assume that expectation of u 1 t is equal to expectation of u 2 t equal to expectation of u 3 t is equal to 0. Then covariance between u 1 t and u 2 t is equal to 0, covariance between u 1 t and u 3 t is 0, covariance between u 2 t and u 3 t is 0. So, all the 3 equations have uncorrelated disturbances. Then the matrix formed by the coefficients of the endogenous variables is the following triangular matrix. Say in the first equation you have 1 0 0, in the second equation you have minus beta 2 1 1 0, in the third equation you have minus beta 3 1 minus beta 3 2 1. Say in the first equation you have just y 1, the coefficient of which is 1. In the second equation, if you take this beta 21 y 1 t towards the left hand side, then you get minus beta 21 y 1 t plus y 2 t. So, the coefficient of y 1 t is minus beta 21 and coefficient of y 2 t is 1, coefficient of y 3 t is 0. In the third equation, if you take these two terms involving y 1 t and y 2 t towards the left hand side, then the coefficient of y 1 t is minus beta 3 1, coefficient of y 2 t is minus beta 3 2 and coefficient of y 3 t is 1. So, the matrix B is of this form. So, this matrix B is a triangular matrix. All the elements of this side, this half are 0. Such kind of models are called recursive models or triangular models. Triangular models because the matrix B is a triangular matrix, and recursive models because the endogenous variables are appearing in different equations recursively. Y 1 appears in the first equation, y 1 y 2 appear in the second equation, y 1 y 2 y 3 appear in the third equation. So, the endogenous variables are appearing recursively in different equations. So, this system of equations is also called recursive system of equations or recursive model. Now, the equation 1 has only exogenous variables on the right hand side as explanatory variables, and all these exogenous variables are uncorrelated with the disturbance term u 1 t. So, you do not have any problem of correlation between explanatory variables and the disturbance term, and you can directly apply OLS procedure for estimating this equation or for estimating the parameters of this equation. Now, we look at the equation 2. Equation 2 contains endogenous variable y 1 t as an explanatory variable. So, on the right hand side as explanatory variable you have y 1 t, but u 1 t which affects y 1 t is uncorrelated with u 2 t. So, notice that the stochastic or random part of y 1 t is u 1 t and u 1 t is uncorrelated with u 2 t, and this implies that the covariance between y 1 t and u 2 t is equal to 0. So, although in the second equation we have y 1 t towards the right hand side as one of the explanatory variables, and y 1 t is an endogenous variable, but it is uncorrelated with u 2 t, and then you can easily apply the OLS procedure, and the OLS procedure will lead to the consistent estimator for the regression parameters. Then we consider equation 3. In equation 3, again on the right hand side you have y 1 t and y 2 t as explanatory variables, but y 1 t depends upon u 1 t and u 1 t is uncorrelated with u 3 t. So, y 1 t is uncorrelated with u 3 t. Further, y 2 t is also uncorrelated with u 3 t. So, you can apply OLS for estimating the parameters of equation 3. So, although in recursive models you have different endogenous variables on the right hand side as explanatory variables, but those endogenous variables are uncorrelated with the corresponding disturbance term. So, you do not face any problem of correlation, and you can easily apply the OLS procedure, and the least square estimators are consistent. In fact, in this model y 1 affects y 2, but y 2 does not affect y 1. Similarly, y 1 y 2 influence y 3, but y 3 does not influence y 1 and y 2. So, in recursive systems of equations, OLS can be applied to each equation separately. You can estimate each equation separately by applying the OLS procedure. Another example of recursive system of equations is, say, you have price equation P t plus gamma 1 0 plus gamma 1 1 W t minus 1 plus gamma 1 2 R t plus gamma 1 3 L t equal to U 1 t. And then you have wage equation W t plus gamma 2 0 plus gamma say 2 4 U t plus beta 2 1 P t equal to U 2 t. Here P is the rate of change of price per unit of employee, W is the rate of change of wage per employee, R is the rate of change of price of capital, L is the rate of change of labor productivity, U is unemployment rate in percentage. Now, you can write this model as, say, 1 0 beta 2 1 1 P t W t. P t and W t are endogenous variables. In the first equation, W t does not appear. In the second equation, both W t and P t appear. Plus, then you have gamma coefficients here, say gamma 1 0, gamma 1 1, gamma 1 2, gamma 1 3, and then the coefficient corresponding to U t is 0 here, and then you have gamma 2 0, 0 0 0, gamma 2 4, and then you have 1 W t minus 1 R t L t U t here equal to U 1 t U 2 t. So, again this matrix, if you write this matrix as B, then B is a triangular matrix, and you have a recursive system of equations. Now, we consider the general form of recursive or triangular model. So, your model is, say, B y t plus gamma x t equal to U t. So, this is just like the simultaneous equations model, but here the matrix of coefficients of y t's B is either upper or lower triangular. Then this system of equations is called the triangular or recursive system of equations. So, B is of the form of a triangular matrix. It may be upper triangular matrix or lower triangular matrix. Or you can say the model is of the form, say, y 1 t equal to g 1 x t plus u 1 t. So, y 1 depends upon x t's. It does not depend upon y 2, y 3, so on y m. Y 2 t is equal to, say, g 2 y 1 t x t plus u 2 t. So, y 2 t is affected by y 1 t and x t's, but y 2 t is not affecting y 1 t, and so on. Y m t is equal to g m y 1 t y 2 t, so on y m minus 1 t x t plus u m t. So, y 1 y 2 y m minus 1 along with x's are affecting y m. but y m is not affecting any of these variables y 1, y 2, y m minus 1. And in this particular case, actually g j y 1 t so on y j minus 1 t x t is equal to beta j 1 y 1 t plus so on plus beta j j minus 1 y j minus 1 t plus gamma x t. So, in different equations y's are appearing recursively. So, the determination of variables is recursive in the sense that y 1 affects y 2, but y 2 does not affect y 1. Y 1 and y 2 affect y 3, but y 3 does not affect y 1 and y 2, and so on. So, the determination of variables is recursive in this sense. And the matrix of coefficients of endogenous variables is of this form. Say it has 1 beta 2 1 so on beta m 1 0 1 so on beta m 2 and so on. So, it is a triangular matrix, lower triangular matrix. So, that is why this system of equations is also called triangular model. It may be an upper triangular matrix also. So, even if B is upper triangular matrix, it is called recursive system of equations. So, if actually B is upper triangular matrix, then y m will affect y m minus 1, but y m minus 1 will not affect y m. Y m and y m minus 1 will affect y m minus 2, but y m minus 2 will not affect y m and y m minus 1 and so on. So, that relationship is also recursive, and then we can apply OLS to each equation separately for estimating the parameters. Now, we consider limited and full information estimation. Actually, in simultaneous equations model, in all you have capital M equations. So, you have two possible options. You have first equation, second equation and so on, mth equation. So, either you estimate the parameters of each of these equations separately. So, you apply some procedure for estimating the parameters of first equation. You apply some procedure for estimating the parameters of second equation and so on. This is one option. Such kind of estimators are called limited information estimators, or these estimation procedures are called limited information estimation. So, in limited information estimation, only the information specific to the equation under investigation is utilized in the estimation process. And this limited information estimation procedures include the indirect least squares ILS, the two stage least square estimation procedure 2SRS, or limited information maximum likelihood estimation procedure. In this lecture, actually we are going to discuss the indirect least square estimation procedure. The second option is, instead of estimating the parameters of each equation separately, you consider all the m equations simultaneously, and then you attempt to estimate the parameters of all the equations jointly or simultaneously. Such kind of estimators are called full information estimators. So, in full information estimation, information present in other equations and the fact that structural disturbances of various equations may be correlated is utilized in the estimation process. And these estimation procedures include 3-stage least squares or full information maximum likelihood estimators. Now, the disturbances of different structural equations may be correlated with each other, and correlated means, say, second equation may have some information about the first equation also, or the third equation also. So, such kind of information present in other equations and the fact that the structural disturbances of various equations may be correlated is utilized in the estimation process. It is just like what we do in seemingly unrelated regression equations model. In seemingly unrelated regression models, you have two options. Either you apply OLS procedure to each equation separately, and then different equations may be correlated with each other, or disturbances of different equations may be correlated with each other. And correlation means the information about a particular equation may be contained in other equations also. So, then we may combine all the equations and then we apply GLS procedure. So, we estimate the parameters of all the equations simultaneously in seemingly unrelated regression models. So, we consider the estimation of a just identified equation, and for estimating the parameters of a just identified equation, we apply the method of indirect least squares. The steps for the estimation are: first we obtain the reduced form equations, then obtain OLS estimates of reduced form coefficients. Then you can easily apply OLS procedure for estimating the parameters of reduced form coefficients, because in the reduced form as explanatory variable you have just predetermined variables which are uncorrelated with the disturbance term. So, the OLS procedure leads to the consistent estimators. Then, if the equation is just identified, then there is 1-to-1 correspondence between the structural and reduced form coefficients. You can solve the relation between structural and reduced form coefficients to obtain unique solutions for structural parameters. And since you have estimates for reduced form coefficients, you can use those relations to obtain estimates of structural parameters. So, we obtain the estimates of structural coefficients from the estimated reduced form coefficients. So, this is the basic procedure for indirect least squares. Obtain the reduced form equations, then estimate the reduced form coefficients by applying the OLS procedure, and then make use of the relationship between structural parameters and reduced form coefficients to obtain estimates of structural parameters. And if the equation is just identified, then you get unique solutions for structural parameters. Again, we consider this example. You have demands function and supply function. You can easily verify that the demand function is unidentified and the supply function is just identified. So, using rank and order conditions, you can easily verify it. So, you cannot estimate the parameters of demand function because it is unidentified, but you can estimate the parameters of supply function because it is just identified. Here Q and P, these are the quantity and price, and these are endogenous variables. X is say the income and this is an exogenous variable. So, we solve these two equations for Q and P, and then you can easily obtain the solutions for P and Q, and you obtain P equal to pi naught plus pi 1 x t plus V t, Q t equal to pi 2 plus pi 3 x t plus W t. And then the values of pi naught, pi 1, pi 2, pi 3 are pi naught equal to beta naught minus alpha naught upon alpha 1 minus beta 1, pi 1 equal to minus alpha 2 upon alpha 1 minus beta 1, pi 2 equal to alpha 1 beta naught minus alpha naught beta 1 upon alpha 1 minus beta 1, and pi 3 equal to minus alpha 2 beta 1 upon alpha 1 minus beta 1. So, you just equate these two equations, demand function and supply function, solve it for P. So, you get this equation and then substitute this value of P into any of these two equations and then solve it for Q. So, you get this second equation. Then we can apply the OLS procedure for estimating pi naught, pi 1, pi 2 and pi 3. Now, suppose small x t denotes capital X t minus x bar, means small x t is the deviation of capital X t from respective mean. Similarly, small p t denotes the deviation from mean of capital P t, and small q t denotes the deviation from mean of capital Q t. Then obviously, the OLS estimator of pi 1 is, say pi 1 head is equal to, we apply OLS procedure to this equation. So, obviously, this is equal to summation small p t small x t upon summation x t square, and pi naught head is equal to p bar minus pi 1 head x bar. Similarly, you can obtain pi 2 and pi 3 in all the estimators of pi 2 and pi 3 also. So, ultimately we get these estimators of pi naught, pi 1, pi 2 and pi 3. Now, the first equation is unidentified and you do not get solutions for alpha naught, alpha 1 and alpha 2 from here, but you can solve these relations for beta naught and beta 1. So, you can easily verify that beta 1 is equal to pi 3 upon pi 1. So, beta 1 is equal to pi 3 upon pi 1. So, what we do in this relation, we replace pi 3 and pi 1 by their estimators, and then this gives you the indirect least square estimator of beta 1. Further, beta naught is equal to pi 2 minus beta 1 pi naught. You can easily verify it if you take pi 2 minus beta 1 pi naught, you multiply pi naught by beta 1 and then you subtract these two, you obtain beta naught. So, to obtain indirect least square estimator of beta naught, what we do? We replace pi 2 by pi 2 head, pi naught by pi naught head and beta 1 by beta 1 head, and beta 1 head is equal to pi 3 head upon pi 1 head. So, basically beta naught head is equal to pi 2 head minus pi 3 head upon pi 1 head into pi naught head. So, this is how you get the indirect least square estimators of beta naught and beta 1. What we have done? First, we have obtained the reduced form equations, then these are the relations between structural parameters and reduced form coefficients. Then we have applied OLS procedure for estimating these reduced form coefficients pi naught, pi 1, pi 2, pi 3, and then we use those relations between betas, alphas and pi's to get these estimators. Now, in fact, you cannot solve those relations for alphas because the demand function is unidentified. So, you cannot estimate the parameters of the demand function. Now, we consider this general structural model. So, at time t, you have the relation b y t plus gamma x t equal to u t, t taking values from 1 to n. So, you have n observations. Now, we write capital Y equal to y 1 dash, y 2 dash, so on y n dash. So, basically this capital Y is n cross capital M matrix of observations on endogenous variables. Similarly, we define capital X equal to x 1 dash, so on x n dash. We take transpose of all these x t's, say we take transpose of x 1, transpose of x 2, so on transpose of x n, and then we write all these row vectors in this form. So, you get this capital X matrix which is of order n cross capital K. So, capital X is n cross K matrix of observations on predetermined variables. Then we define capital U equal to U 1 transpose, U 2 transpose, so on U n transpose. Now, each U t is of order m cross 1. So, U t transpose is of order 1 cross m. So, capital U is of order n cross m. Capital U is the matrix of disturbances, and then we can write equation 1 as capital Y B transpose plus x gamma transpose equal to capital U. Now, suppose you want to estimate the parameters of the first equation. Of course, I am giving you this method of indirect least squares for estimating the parameters of first equation, but you can apply the same procedure for the ith equation also, or simply you have to replace this 1 by the corresponding subscripts. Then expectation of u 1 is 0, expectation of u 1 transpose is taken as sigma 1 1 I n. Here y 1 is of order n cross 1. So, this is the vector of observations on endogenous variable in the equation. Then capital Y 1 is of order n cross m minus 1. So, this is the matrix of observations on other m minus 1 endogenous variables in the equation. So, apart from y 1 you have these small m minus 1 more endogenous variables in the first equation. X 1 is of order n cross k. So, this is the matrix of observations on k predetermined variables in the equation, and u 1 is n cross 1 vector of disturbances. Further, we obtain the reduced form of this equation. The reduced form of this equation is, say, y equal to minus x gamma transpose B transpose inverse plus u B transpose inverse, and then you can write it as x times B inverse gamma transpose plus u B transpose inverse, and then you have minus sign also here. So, then we are writing minus B inverse gamma equal to pi. So, you get x pi transpose plus V. V is equal to u B transpose inverse. So, we get the reduced form y equal to x pi transpose plus V. Here pi is minus B inverse gamma, V equal to u B transpose inverse. Then we apply OLS for estimating the reduced form coefficients here. So, this gives the following estimators of pi transpose. Say pi hat transpose equal to x transpose x inverse x transpose y. You simply apply the OLS procedure for estimating pi transpose in this equation. So, now you have got the OLS estimator for the reduced form coefficients. Then we can write the equation 3, which is y 1 equal to capital Y 1 beta plus x 1 gamma plus u 1 as, say, small y 1 capital Y 2 x 1 x 2, and then corresponding to small y 1 you have 1, corresponding to capital Y 1 you have minus beta, you take minus y 1 beta towards the left hand side, then you can take y 2 into 0 here, minus x 1 into gamma minus x 2 into 0 equal to u 1. So, you get y 1 capital Y 1 from here, capital Y 2 x 1 x 2, and corresponding coefficients are 1 minus beta 0 minus gamma 0. So, you get this equation. Capital Y 2 and capital X 2, these are the matrices of observations on endogenous and predetermined variables excluded from the equation. You are not including these endogenous variables or these predetermined variables in the first equation. So, that is why you have taken the corresponding coefficients as 0. The first equation includes, say, this small y 1 and the endogenous variables contained in capital Y 1. You have small m minus 1 endogenous variables contained in capital Y 1, and then you have small k minus 1, small k actually predetermined variables contained in x 1. Then the relation between the structural and reduced form parameters is pi transpose B transpose equal to minus gamma transpose. You get this relation from here. You have actually B pi equal to minus gamma, or pi transpose B transpose equal to minus gamma transpose. Then corresponding to the coefficients of the structural equation 3, this relation is say pi transpose, then you have 1 minus beta 0, say corresponding to the first equation, you have these coefficients in B transpose, and corresponding to gamma transpose you have, or minus gamma transpose you have these coefficients. So, you get the relation pi transpose 1 minus beta 0 equal to gamma 0. So, this is the relation between original structural parameters and reduced form coefficients corresponding to the first equation, the equation in which we are interested. We want to estimate the coefficients of the first equation. So, what we have to do? We replace this pi transpose by its OLS estimator. The OLS estimator of pi transpose is x transpose x inverse x transpose y. And then we have 1 here, and we denote the indirect least square estimator of beta by B, say. And then we have 0 here, we denote the indirect least square estimator of gamma by C, say. So, you get C is 0 here. Then you have to solve this equation for B and C to obtain indirect least square estimators of beta and gamma. Or you can write it as x transpose x inverse x transpose, then we write y equal to small y 1 capital Y 1 capital Y 2, because this y is equal to y 1 capital Y 1 capital Y 2. Then you have 1 minus b 0, here you have c 0, and then we multiply these two. So, you get x transpose x inverse x transpose y 1 minus x transpose x inverse x transpose capital Y 1 b. You get y 1 into 1 minus capital Y 1 into b plus y 2 into 0 here. So, finally, you obtain this equation equal to C 0, or x transpose y 1 b. You take this, you multiply both sides by x transpose x. So, you get x transpose y 1 minus x transpose y 1 b equal to x transpose x C 0. Or you can write it as x transpose x C 0, here you have, plus x transpose y 1 b, here you have, equal to x transpose small y 1. Then further we write capital X equal to x 1 x 2. So, x transpose x is equal to x 1 transpose x 1, x 1 transpose x 2, x 2 transpose x 1, x 2 transpose x 2. And x transpose y 1 equal to x 1 transpose y 1, x 2 transpose y 1. So, you can solve it and you get x 1 transpose y 1 b plus x 1 transpose x 1 c plus you have x 1 transpose x 2 into 0 equal to, again you have x transpose small y 1 equal to x 1 transpose y 1 x 2 transpose y 1. So, this is equal to x 1 transpose y 1. Further, you have x 2 transpose y 1 b plus, then you have x 2 transpose x 1 c plus x 2 transpose x 2 0 here. So, you get x 2 transpose x 1 c equal to x 2 transpose y 1. So, you get these equations. And then we get unique solutions for B and C if the condition for exact identification is satisfied. So, if this equation is, the first equation is exactly identified, then we can solve it for B and C and we get unique solutions for B and C. Now, suppose you write delta equal to beta transpose gamma transpose whole transpose, or in fact, delta is equal to beta gamma, and you write z 1 equal to y 1 x 1. Then the indirect least square estimator of delta is given by, say, delta head equal to B c equal to x transpose z 1 inverse x transpose y 1. Just you combine these two equations and then you write delta head equal to B c. So, after some manipulations and using these notations, we can write delta head equal to x transpose z 1 inverse x transpose y 1. Now, this is somewhat like instrumental variable estimator. Now, suppose you write the equation, the first equation as y 1 equal to capital Y 1 beta plus x 1 gamma plus u 1. We write this equation as y 1 equal to z 1 delta plus u 1, where z 1 is equal to capital Y 1 capital x 1, delta is equal to beta gamma. So, we write this equation as y 1 x 1 beta gamma plus u 1, and then we are writing this equal to z 1 and this equal to delta. Now, suppose W is n cross m plus k matrix such that the probability limit of n inverse W transpose Z 1 is equal to sigma W Z. This is a finite non-singular matrix. Probability limit of n inverse W transpose U is 0 and probability limit of n inverse W transpose W is sigma W W, a positive definite matrix. Then instrumental variable estimator of delta is, we are using this matrix as the matrix of instrumental variables, and the instrumental variable estimator of delta is W transpose Z 1 inverse W transpose Y 1. And under these conditions, you know that the instrumental variable estimator is a consistent estimator and its asymptotic covariance matrix is of the form, say sigma 1 1 by n, the probability limit of n inverse W transpose Z 1 inverse, n inverse W transpose W, n inverse Z 1 transpose W whole inverse. And then we substitute the values of all these probability limits. So, you get sigma 1 1 upon n, sigma W Z inverse, sigma W W, sigma Z W inverse. So, this is the asymptotic variance covariance matrix of instrumental variable estimator. And here a consistent estimator of sigma 1 1 is, say, S 1 1 equal to 1 upon n y 1 minus Z 1 div transpose y 1 minus Z 1 div. Then we consider a generalized least squares estimator. Say we pre-multiply equation 9 by x transpose and then we get x transpose y 1 equal to x transpose Z 1 delta plus x transpose u 1. If we apply OLS to this equation, we get delta head equal to x transpose Z 1 inverse x transpose y 1. So, we get the indirect least square estimator. Further, we observe that the covariance matrix of X transpose U1 is sigma 1 1 X transpose X. You can easily verify it. So, the covariance matrix of U1 is sigma 1 1 I. So, the covariance matrix of X transpose U1 is sigma 1 1 X transpose X. Now, suppose we apply GLS to equation 10, then what we get? So, you denote it by delta curl equal to, you have matrix X transpose Z1 here. So, we take X transpose Z1 transpose. So, you get Z1 transpose X. Then you have inverse of this variance covariance matrix, you get X transpose X inverse. Sigma 1 1 will actually cancel out if you consider both of these two terms. Then X transpose Z1 whole inverse, then Z1 transpose X, X transpose X inverse, X transpose Y1. We are simply applying the generalized least square procedure to equation 10. We get this estimator. Here Z1 is of order n cross m minus 1 plus k, and X is of order n cross k. So, finally, this matrix is of order m minus 1 plus k cross m minus 1 plus k, and you can take inverse of this matrix if this matrix is non-singular, and a necessary condition for this is m minus 1 plus k less than or equal to capital K, or m minus 1 less than or equal to k minus small k, and this is the order condition for identification. For just identified case, Z1 transpose X is of order m minus 1 plus k cross m minus 1 plus k, and then you get this expression for delta curl, which is the indirect least square estimate. So, actually in this case, all these matrices are square matrices and non-singular, and then you can take inverse of this. So, you get X transpose Z1 inverse X transpose X, Z1 transpose X inverse, and then you have Z1 transpose X, X transpose X inverse Y1, and finally, you obtain, say this is identity matrix, then you get this as identity matrix, and finally, you get this expression, which is equal to delta hat, the indirect least square estimator. So, we have discussed the recursive models. In recursive models, different endogenous variables appear in different equations successively or recursively. In recursive models, you do not face any problem of identification, and you can apply OLS procedure for estimating the parameters of different equations separately. Then we have also discussed the method of indirect least squares. We can apply the method of indirect least squares when a particular equation is just identified. In that case, we estimate the parameters of reduced form equation using the OLS procedure, and then we use the relationship between structural parameters of that particular equation and reduced form coefficients for obtaining the indirect least square estimators. Next lecture, I will discuss more estimation procedures like two-stage least square, limited information, maximum likelihood estimator, and other estimation procedures. So, I am going to stop here. Thank you.